Okay, let's look at the first problem now. So problem 1 for me, we're given a demand equation that looks something like this for my numbers. It's 50 exponential to the negative 0.02 p. So see, this is a relationship between q and p. So we know it's a demand relationship. And now we'll have to figure out the elasticity at 40 units. Okay, so how we begin this problem is we know that the elasticity as a function of p is defined to be times p over q, right? So the first step would have been to actually solve for dq over dp from the given equation. Let's do that. So dq over dp, you have to take a derivative of this equation up here, which would mean you're going to keep 50 as it is. Derivative of an exponential is just that thing, but because of chain rule, you have to multiply by negative 0.02. So this is the derivative. So when we finally compose the whole thing, we're going to write elasticity is going to be that thing, 50 times p divided by q. So now in order to make this a whole function of p, we need to substitute for q from this relationship. So you're going to pick that value and just put it down there. So now when you see that clearly, the denominator and this term in the numerator are just going to cancel each other out. So our elasticity is going to be literally just negative 0.02 times p. And now because they ask us to evaluate the elasticity at 40, so E of 40 will just be plugging in 40 into that p. So I get negative 0.02 times 40. I'm not going to solve it here, so you can punch these numbers as it is. And that's the answer for the first one. Okay, let's go to the second problem. Kind of similar, same kind of approach. In this case, our demand equation looks like a straight line. So A minus BP, which represents a straight line where A and B are constant. So the slope of the line, according to this, will be negative B, and the intercept where it cuts is going to be A, because if you compare it to the straight line, you'll get the same results. So now, in order to define elasticity, first of all, let's go back what they want us from this problem. They want us to solve dE over dP, and the second derivative of elasticity. So in order to do that, we have to first of all solve for the elasticity of the function, right? So we also know, again, same fact, that elasticity is defined as dq over dp times p over q, right? So now from this equation, when you try to take a derivative, what do you get? A is a constant, so that's 0. Minus b, b is also constant, times p. So we're taking a derivative with respect to p. What we'll end up with is just negative b. Awesome. So now the elasticity function could be easily defined as dq over dp, so negative b times p over q. So we have to replace q from this equation. That's going to be a minus bp. So if you simplify a bit, you get negative bp over a minus bp. So you're going to keep that handy, and we're going to move on to the steps where we have to find the derivative of this function and the second derivative. So I'm just going to put it down here for reference. If that's the function of p, you see p in the numerator, p in the denominator. So we got to use chain rule to be able to find that thing. So dE by dP, using the chain rule, what you do is you'll square the denominator keep that as it is for the first time, times the derivative of the numerator is just going to be negative b, minus, you got to keep negative bp as it is this time, and the derivative of the bottom part is a minus bp is also just negative b. So when you resolve it a little bit, you don't have to do so because we're going to take a second derivative of this function, so it's better to have it like in the simplified form because then it gets easier. So if you clear that up, you get, on the first time you get negative ab, you get positive b squared p. You have a negative bp times a negative b, so you get a positive b squared p, but because of this extra negative outside, this will become negative b squared p. So you see these guys will go away from each other. So now our dE over dP, the first answer to this problem, will just be, oops, I gotta get rid of this one at the bottom. It's just negative AB over A minus BP whole squared. So that's the answer for the first one. So now when you're supposed to take a second derivative of this function here, how would you do so? We're just going to take this function and start deriving it again. So now in this case, you see the numerator is just a constant. It doesn't have a p there. And you only have p in the denominator, so what we can do is we can use a neat trick. The fact I'm going to mention here is if your f of x looks like 1 over x to the power of n, some function like this, then the derivative of that function is just going to be negative n over x to the power n plus 1. How? You can see for an example, if your function is, let's say, 1 over x to the 5, right, then the derivative of that function will just be negative 5 over x to the 6. You can verify yourself for this one using the rule that you learned for the power rule. So using that fact, I know the bottom part is just a function of x. What I can do is I can keep the constant outside, so d squared e by dp squared. You got to keep negative ab outside because it's just a constant, times the derivative of 1 over a minus bp whole squared, which will give you minus 2 over a minus bp cubed, because you got to raise the power by 1, so we did that. Now I have to multiply by the derivative inside because of chain rule. Okay, so derivative of a minus bp is minus b. So when you simplify, you see you have 1 negative, 2 negatives, 3 negatives, so the overall answer will be negative. So let me just remove that. dp squared is just going to be negative 2ab squared over a minus bp cubed. And that's the answer for the second part. So now, the last part of this problem is asking for you to pick a graph that suits the best for the elasticity function. So you remember the elasticity function looks like this. It's a negative bp over a minus bp. So now, when you think about it, price can never be negative. So this function is inherently negative because of this negative sign in front of it, which means there could be no possible b values that can ever turn it positive. So what we're trying to have here is a graph that will go down like this. So you'll have to have a negative graph. So I'm going to pick that blue color, and it goes like this. So option D in our case is the correct option for the graph of this function, because it's always going to be below the x-axis. Okay, so now let's talk about problem number 3. So now again, it's a very similar problem. Now in this case, we have an implicit equation that describes the relationship between the demand. So let's see that. For me, those numbers are ln Q, negative 1, ln P, plus 0.02p equals to 7. So we're going to take the same approach. All we got to do is to find the elasticity of this function. We have to find dq over dp, which we'll solve in this equation using implicit differentiation. Okay, so we're taking the derivative of this whole equation with respect to p. So derivative of ln q with respect to p will just be the derivative of ln q with respect to q. That's going to be, hold on, not that. It's going to be 1 over q times dq over dp because of implicit differentiation. Similarly, derivative of ln p is just going to be 1 over p, and derivative of 0.02p is going to be 0.02. And on the right side, because of 7, you have a 0. So from there, if you isolate for q, actually dq over dp, then what you get is q times 1 over p minus 0.02. Okay, so once we figure that out, now the elasticity of the function is going to be defined by just multiplying dq over dp that you got. That's that thing. Times p over q. So you cancel these q's right away. So our elasticity, when you simplify it, will just become 1 minus 0.02p. Now the second part of the problems is going to talk about the max revenue. The fact that I want to mention here from economics is revenue is maximized when you're perfectly unit inelastic, which means your elasticity function of p must be equals to -1. So if that's true, to figure out the p which gives you the maximum revenue, all you got to do is equate the EP that you found out to -1 and solve for p. So if you do that, you get 1.0002p equals to -1, and then p will just be -2 over 0.02. So you can submit that as it is. Okay, let's talk about problem 4 now. So problem 4 is going to involve some concepts that we talk about in economics. This problem is acting weird, so I'm going to put a disclaimer here that it might not work. Sometimes it does, sometimes it doesn't. For the people that I've tried with the numbers, it does. But the way you should kind of solve it will make sense when we talk about it. You'll see why. I don't know, not quite sure why it doesn't work, but let's see. It's going to be good if it works for you. If not, then you got to let the TA know, and anybody you can seek help from, right? So let's see. In this question, they have a person called Nick who has lost faith in the bank, and he decided to diversify his portfolio by keeping some money under his mattress. So the dollar in the mattress, in my case, it's going to be $5,000. And then the rest in the GIC in the bank, so dollar in a GIC is actually $2,000, which is going to be giving him a 4% interest compounded continuously. Okay. Now, what we have to do from this point onwards, we have to figure out the actual value. And what they're asking for the first time is the equation for I of t. Okay. So I of t is the total real value of the investment after t years. So we got to analyze the situation in different cases for these two money values. But there's a little thing that we have to mention before that. The inflation is also happening. So inflation rate in my values is just 2%. So one way to look at inflation is the way you can just see that it's just acting as a negative interest. So a negative interest will automatically just depreciate your value. Okay, so the money that has not been earning interest will always be under the influence of the inflation, and it will be reducing the value. So we're going to start talking about the dollar value. The investment is going to be, so the dollar money in the bank after t years plus the dollar money in the mattress. So actually after 2 years. So once that happens, you know the bank value will just be the principal amount, $2,000, compounded continuously at 4% rate, which just means e to the power of 0.04t. So that's the formula for continuous compounding. So once that happens, the other money will not change because it's going to stay there. So this right here is the investment without inflation. So because the inflation is also going to be there, your value of the money is going to reduce by 2% after each year. So if your value is being reduced after each year, all you're going to be left with, so you take that, all the money that you got, that you earn interest in the bank, that's in the matrix, is going to reduce its value by a little bit. So it's 2%, so the actual value you'll be left with is going to be 1 minus 0.02 to the power of t. So think about that for a second. Once the first year passes by, you earned that much money here, so the interest on the GIC will be earned in the investment by 2,000 times e to the negative e to the 0.04, and the 5,000 will stay like this. All of the money that you have here will be under the influence of inflation. So now, if the inflation is 2%, you can see that as everything else is getting more expensive by 2%, or you can see it as the effective value of your money is being reduced to 98%. So that's why you have 1 minus 0.02 times to t. Because after 1 year, all the money value you have will be reduced down to 98% of its effective actual value, and will keep on going down from there. So the actual I of t expression is just going to be that term. So it's 2,000 e to the power 0.04t times, I'm going to multiply 0.98 to the power of t plus that remaining 5,000 times 0.98 to the power of t as well. And so this is the function that we're going to be working on with. Okay, that's the first part of the problem. Now, what I want to see is figure out the number of years when you see the value is going to hit a minimum. Okay, so to be able to figure that out, we need to learn a concept of calculus where we have to find a critical point. So for any function, the minimum or the maximum value of that thing lies on something that we call critical points. Those critical points are something we're going to talk about on the next page. Okay, so now when we're going to talk about how to find the minimum of a function, we got to talk about how we distinguish whether a function will have a max or a min. So just a little example, I'm going to write it in a different color right now. So what we're going to do is just in pink, it's just a fact. So when you see a random function go like this, right? If it's defined over that axis, wherever you see a max and a min, so let's say about you see a max and min right there in the graphic view. So we could just say that this point right here is a max, and this point right here is a min. What does that suggest about the function? Well, if you were to draw a tangent line just before the max, that would look something like this, that has a positive slope, right? And if you draw a tangent line just right after that, you have a negative slope, which means it's slanting downwards. But at the very point we observe is the slope of the tangent is going to be 0. So again, the same case here as well. When you draw a tangent at the minimum, what you see is the slope is 0. Any point after that, you have a positive. Any point before that, you have it negative. So a function will always have a max and a min if the slope is equals to 0. Okay, So essentially, if at any point, let's call that point C, we observe that the derivative of the function, which is f prime, at C is 0, then we call C the critical point. And we know f of C, which means the value of the function at C, will either be a max or a min. So in order to figure out whether it's going to be a max or a min, so as you observed over there for the graph here, let's call that one this point A. So right now we can clearly see there's a maximum of a function at A. Okay, given that fact, what you can say is f of A is a max, so you have to observe the behavior of the slope as you sweep across it. So if you're just before A, what you observe is the tangent was positive, so a positive tangent, and then right at A, the tangent was 0, which means it's horizontal, slope was 0. And now when you pass that point, after that the slope becomes negative. So you see that kind of a shape. When you draw it out, you see that kind of a shape, right? The tangent will depict that kind of shape. So this kind of depicts that this will have a maximum if you have that shape. So if the derivative before the point was positive, became 0 at the point, and then became negative, you can conclude that you have a maximum. And for the minimum, it will be the other case. So let's say at this point, we're talking about the minimum point now. So let's say at that point you have it a minimum here at B. So we can say have a minimum here. We have to observe is the slope just before that thing. We saw it was a negative slanting slope. At B itself, it was just horizontal. And then right after any point in that, you have it this way. So now if you observe the flow of the function around that point, as we did that in that one, we see that we'll get a minimum. This behavior and all the talk that we did about this is formally known as the first derivative test. Okay, so this is the first derivative test. We're going to talk about the second derivative test in the future questions. But right now, coming back to the main problem, what we're trying to talk about is we had our IT function, right, which we talked about. This was 2000 e to the power 0.04 t times 0.98 to the power of t plus that number e to the 0. No, it's just gonna, my bad. Should just have 0.98 to the power of t. So now in order to find the minimum time, we know the minimum time will happen when you have this condition happening here. The derivative must be 0. So what we have to do is we have to solve for the points where the derivative of this function I of t is 0. Okay, so we have to compute the derivative first, and then we can do the analysis later on. So let's try to compute that. We know we got to use the fact. Okay, I'm just going to mention it out here. The fact is, if you have a function that looks like this, a to the power of x, okay, where a is some constant, the derivative of that is going to be a to the x ln a. We're going to use the fact to find the derivative of this term here because it looks exactly like that. So let's flip to the next page and start working on it. It's going to copy down function quickly so we can t plus to the power of that, right? So we're going to take a derivative of this. You got to use a product rule in the first piece because it's two functions being multiplied. So when you do so, the derivative will be this times e to the 0.04 t times the derivative of the top is 0.04. We're going to keep that number as it is, plus, now keeping the first person as it is, we have this e to the 0.04 t multiplied by the derivative of 0.98 to the power t, which will give you 0.98 to the power of t times ln of 0.98. So that is the derivative of the first piece. And now the derivative of the second piece, which is 5,000 times 0.98 to the power of t, will just be, I'm just going to remove that, plus 5,000 will stay as it is, times 0.98 to the power of t times ln of 0.98. Okay, that's pretty ugly. We have a lot of terms. What we can see is on top of our eye, we can eyeball it, and we see that 0.98 to the power t is a common factor for a lot of them. So let's factor that out. Oops, add that extra over there. When you do so, you get 0.98 to the power of t, and in the between you'll have this whole term, which is 2,000 e to the power of 0.04 times 0.04. That's from the first term. From the second term, we'll get the same exponential, 2,000 e to the 0.04 t, but this time this is multiplied by ln of 0.98. So that's from these first two terms. The last term will only have a plus 5,000 times ln of 0.98. Okay, so once we got this nicely factored out, we were trying to figure out which points of t are going to make it equals to 0 to find the critical points, right? The critical t is going to be that value. So let's try to figure that out. When you see that, when you equate that equals to 0, because this part is an exponential will never give you 0 values. So you're going to ignore that part. We're only going to consider the factor that's multiplied with it. So we're going to make this whole thing equals to 0. I know it's going to be a little bit longer, but let's see what happens. Once you do so, what would you get is, out of that, if you see closely, you can say this 2,000 times 0.04 times e to the 0.04 t. We're missing a t on the top. My bad. This plus e to the 0.04 t times ln of 0.98 must be equals to, you send that 5,000 times ln times 0.98, we'll just on the right side, so we have negative 5,000 times ln of 0.98. Alright, so now in these two terms on the left side, what you can see is e to the 0.04 t is a common factor, so let's factor that out and isolate for that. So when you do so, again, I'm doing the algebra in my head most of the time, so I recommend you guys to try it out yourself for these versions of your numbers, but that should look something like this. Ln 0.98 whole thing divided by times 0.04 plus times that. So now we have to isolate for t, right? So in order to be able to isolate for t, we got to take log of both sides. So we take ln of both sides, we'll be able to isolate for t, and I'm going to write straight up the answer for that. And you'll see it's going to be this. So from that, t, okay, might as well just do that to make it more clear. When you take ln of e to the power of 0.04 t and ln of all of that, 5,000 times ln of 0.98 divided by 2,000 times 0.04 plus 2000 times ln of 0.98. So once we have the whole expression, let me just double check if it's correct. Yes, it makes sense. So once we have this whole expression out here, because ln of an exponential is just the power itself, so this becomes 0.04t. Well, that whole thing out here, right? I'm just not going to copy it down for now. But then you can ask for t very easily. Well, then t will just be all of that. So ln negative 5,000 times ln of 0.98 divided by 2,000 times 0.04 plus 2,000 times ln of 0.98. This whole thing over 0.04 is a very nasty expression, but this is supposed to be the t value that's going to give us a 0 for the derivative of I of t, like we did on the previous page right here. So now, once we've done that, as we talked about the analysis on the previous page before that, to be able to conclude whether it's a maximum or minimum, we have to observe this behavior. That you have to have a slope that goes negative, then becomes 0, and then becomes positive, right? So you need to observe that thing for those points. But because in this case, what's going to happen here, we're going to use a logical reasoning to answer why the critical point we found out is going to be minimum. So in the function that we're talking about, the investment, let's go back a bit. Let's talk about that a second. If you go back to the main problem, you know the money that he invested in the GIC is being compounded continuously at 4% interest rate, right? So when you see that it's happening at 4% interest rate and the rate of inflation is less than that, you kind of have a feeling that the money will eventually grow to get a bigger quantity than the inflation, because inflation is not going to be able to catch up to the rate of growth of the money, right? If the inflation and the rate of interest was equal, then your money will not change its value. It's not going to either go down or go up. But in this specific case, because inflation rate is below the actual growth rate, we know the money will eventually grow. So the more time passes by, the more the value the money will get. So if you have a critical point in that zone, that has to be a minimum, because it cannot be a maximum, because the maximum value of the money is going to be infinite amount of money as the time passes by. Okay, so with that logic, you can say whatever point you got is going to give you a minimum. Okay, but on the exam and usually in the other cases you have to prove it, but in this case we can just use the logic. Okay, so logic is that I of t will have a minimum because it can't have a max. Oops. And why is that? Because the max value is infinite money, because the GIC is giving you more interest rate than the inflation. So your money is eventually going to grow at the end of the day. Okay, so given that logic, you can use that, and this is the value. So one reason why I solve it symbolically here, all of these values, so that people can actually navigate through the pieces and how they fit along. And I'm a big, I really strongly recommend everybody to just submit this as it is. Okay, because if you start to calculate these values and then put them in decimals, it's gonna get very messy. Okay, it's better to give you the accurate answer. So just try to, it's gonna be a little bit hassle to type it in, but I would recommend you guys try to type it out, or at least work it out in decimals first. And once you have a number in decimals, you can look at to the other one. Okay, so now we are gonna skip problem 5, as most of the TAs said the problem is broken. because there's something wrong with it. So we're going to skip that. I'm not going to talk about that for now. And we're going to jump straight to problem number 6.